Unit 9 is about the properties of solutions, and Part 1 is just the basics of solutions. A solution is a homogeneous mixture of two or more pure substances. In a solution, the solute is dispersed uniformly throughout the solvent. So the solvent dissolves the solute, and the intermolecular forces between the solute and solvent particles must be strong enough to compete with the intermolecular forces between solute particles and the forces between the solvent particles. So what that last part means is that the attraction between the solute and solvent has to be stronger than the attraction of the solvent to itself and the solute to itself for the solute to dissolve. If it's not, the solute is just going to sit in there and not dissolve. So for a solute to dissolve, the solvent needs to have stronger intermolecular attractions to the solute than the solvent molecules do to each other and the solute does to itself. If that's not the case, the solid is just going to sit there. It's not going to dissolve and be the solute. Now, we've seen this illustration before when we're forming solutions, but the solvent molecules are going to pull the solute particles apart and surround them. That's called solvation. Not salvation, solvation. So if we look at an ionic salt like sodium chloride and water, it dissolves because the ion-dipole interactions between the polar water molecules and the sodium and chloride ions are strong enough to overcome the lattice energy of the salt crystal. So if you look at the picture, it's kind of hard to see on this one, but the positive end of the water molecule would be attaching to the negative chloride ions, and the negative end of the water molecule, the oxygen end, would be attracted to the positive sodium ions. So each ion is going to get surrounded by water molecules and pulled apart from the main body of the solid. That's the solvation process. Just because a substance disappears when it comes in contact with a solvent, that doesn't mean that the substance was dissolved. It could mean that the two substances underwent a chemical reaction together. In this example, iron pellets are soaking in concentrated hydrochloric acid, and instead of dissolving the iron, we're ending up with a green product of a chemical reaction. The one way to tell if a substance was dissolved instead of reacting is when a substance dissolves, it disappears and it's dispersed throughout the solvent. If you evaporate all the solvent, you're going to be left with the solute sitting at the bottom of the beaker. So if you boiled a saltwater solution until all the water was gone, you would have all the original salt left at the bottom of the beaker. Saturation is a main property of solutions. A solution is unsaturated if it can still dissolve more solute. If less solute that can dissolve in the solvent at that temperature is dissolved in the solvent. That just means that it's unsaturated, it can have more solute dissolve in it. A solution becomes saturated when it can't dissolve any more solute. It's holding as much solute as possible at that temperature. In a saturated solution, the dissolved solute is in dynamic equilibrium with the solid solute particles. And that dynamic equilibrium is shown over here. In a saturated solution, if you put more solute in, you're not going to see it dissolve, but what's happening, instead of the extra solute just sitting there, you'll have solute being precipitated and dissolved at the same rate. That's what these double arrows mean. For every solute particle that is dissolved, there's one put back onto the main solute mass. So you don't see a change. The mass of the solute stays the same, but it's in dynamic equilibrium. That means there's something always happening, we just don't see it. Solutions can become supersaturated in special conditions when the solvent is holding more solute than normally possible at that temperature. That's usually done by heating a solution and dissolving the solute in it, then allowing it to cool. Supersaturated solutions are unstable. You can cause a supersaturated solution to rapidly crystallize by just adding one salt crystal, or even just getting a tiny piece of glass scratched off the side of the flask or container of the supersaturated solution. So in this picture, they're adding one seed crystal, and as soon as they add that, the rest of the crystals rapidly form out of the solution. Let's talk for a second about solvents. The general rule for making solutions is like dissolves like. That means that a polar solute will be dissolved by a polar solvent, and a nonpolar solute will be dissolved by a nonpolar solvent. If you mix a polar and nonpolar solute and solvent, nothing's going to happen. So this is oil and water. Oil is nonpolar, water molecules are polar. It's just going to look like oil bubbles if you shake it up, or if you just let it sit, the two will separate. They're not going to dissolve because they're not attracted to each other. Gases can actually be dissolved in solvents, and this is usually done by bubbling that gas into a container of that solvent. The solubility of gases increases with the mass of the gas molecule, so the larger the gas molecule is, the more of it's going to dissolve. The reason for that is the increased number of electrons in that larger gas molecule allows for increased London dispersion forces. And that means there's going to be more intermolecular attraction between the gas molecule and the water solvent. As a general rule, solubility of solid solutes in liquid solvents increases with increasing temperature. So if you want to dissolve more solute in a solvent, you need to heat it. As temperature goes up, so does solubility for most substances. You see, for cesium sulfate it actually decreases, but for most common substances, as you heat up the solvent, you're able to dissolve more solute in it. The opposite is true of gases, however. As you increase the temperature of the solvent, you're going to decrease the amount of gas that can be dissolved in that solvent. If you think about carbonated soft drinks are more bubbly if they're stored in the refrigerator, and warm lakes have less oxygen dissolved in them than cool lakes do. So just remember that for solids, solubility goes up with temperature, and for gases it's the opposite. As temperature increases, the solubility of gases will go down. Solubility is usually measured in grams per liter, grams per milliliter, or grams of solute per 100 grams of solvent. And we can use that as a conversion factor in dimensional analysis or even stoichiometry problems. So let's look at this example. Calcium chloride has a solubility of 74.5 grams per 100 milliliters at 20 degrees Celsius. How many moles of calcium chloride are in 250 milliliters of saturated calcium chloride solution? Well, if we know it's a saturated solution, that means it's got the maximum amount of solute dissolved per amount of solvent that we have. So we're going to start with this 250 milliliters of calcium chloride. And we can use the solubility as a conversion factor to go from milliliters to grams. So we know that for every 100 milliliters of calcium chloride solution, there's 74.5 dissolved grams of calcium chloride. And they're asking us to find moles, so now we can hit up the periodic table and find the molar mass of calcium chloride to convert into moles of CaCl2. And the molar mass of calcium chloride is 111 grams per mole. So 250 times 74.5 divided by 100 times 111, that's going to equal 1.68 moles of calcium chloride. Your question for this section: potassium chlorate has a solubility of 7.19 grams per 100 milliliters at 20 degrees Celsius. How could I dissolve 9 grams of potassium chlorate in 100 milliliters of water?